I would like to illustrate this classic linear programming problem here. So first, this is the story you can read, and he has to hold at least 200 books. So let's see how we can do this here. So it has 200 books by having, say, X and Y boxes, right? And X can hold large one, that's 20 books, and Y can hold 10 books. So if you use X and Y not as boxes but number of boxes, then you can hold this many books. And we are going to get into inequality a little later, but for now, let's make it equality. So it's at 200. Okay, so that's what we have. And then second equation here, Hassan must not use more than 15 boxes. So combined boxes, it has to be less than 15. But as I said, I'm going to set at 15 because I'd like to show you a few things here. And he must use at least 3 small boxes. Which is small boxes? Y small box. So I will set at 3 for now. And then the number of small boxes must be less than or equal to the number of large boxes. So the number of small boxes has to be less than or equal to number of large boxes. For this here, I will set equal again. Okay, and then find the least possible cost of all the boxes. I will do this last here, but for now, I'd like to show you these conditions here. So I will do contour plot, and I'm going to enter all those here, and X will go from 0 to 20 boxes, and then Y will be 0 to 20 boxes. Okay, so I got this one here, and I'm going to put these conditions that I was doing here. Okay, so I have this, and then, okay, let me show you what it looks like. That's the function that we just did this here. Okay, here we go. And the second one is this. It may get confusing, so I will give them each one their own line like this. So you will see this. And then the third one, Y is 3. So I will have it here. Okay, it looks like this. And then fourth, Y is equal to X. So I will do comma and here. So these are the conditions here. Being a linear programming, we will look for the area where all of them overlap, and then we are going to go for the edges. Now, why we have to go for the edges, not the middle, it will become clear when I do this part here. But anyway, for now, I'm going to do the turn this into regional plot problem. So here, instead of contour plot, I will do region plot. And I'm going to implement the inequality now. So altogether, he has to hold more than 200 books. So here we go. We had to do this here. Okay. And then the box has to be less than 15. Must not use more than. So first of all, let's see if I can plot this. Can I even plot it? Here we go. So I got still these lines here, but I have this region. So I have to hold, this is how many books I hold. And this region will hold 200 books or more. And here, I have to use less than 15 or equal to. Here, I also got to put equal. Makes no difference in our plot because we cannot see this thin line of x plus y equals 15. But let's do it this way. So this is what we get. So to hold more than 200 books, you need this region, which means you got to have more than 10 boxes or more than some combination of X and Y. And to use less than 15 boxes, you got to have some combination of these here. And so this combination part where they overlap is where the condition is satisfied at the same time. And then must use at least 3 small boxes. So that means I got to be bigger than or equal to 3. So that becomes this. So now the part I want is this. And for the reason that I will show you, the answer we are looking for is either this vertex or this vertex or this vertex. It's always at one of the vertices. And then here, last one was number of small boxes must be less. So Y has to be less than the large one. Bam, here we go. So what do we have? Maybe you didn't see it, but it is this one. It is this region now that we are going to deal with. And then we are going to see who produces the cheapest cost here. Cost didn't enter here, so we are just talking about this region where we are going to see we're going to consider the cost, but we didn't enter the cost yet. So now I'm going to enter the cost and show you where that is. To do that, I'm going to do plot 3D. And I will plot something very mundane, just one here. Okay, and X will and Y will cover the same area as before. Okay, then if I see this one here, you will see the height of 1, you see, is 1 throughout those regions here. But it doesn't end there, of course. What I'm going to do is I will specify where the plot will be. In other words, I want to get this part here. So I will tell Mathematica to draw only that part for me. So that's done with the region function. And then is a function of x, y, and z. Okay, where my x, y, and z are these. So I will copy it and paste it here, except I should have shown you here. 1 second, I skipped one. So now you may say, how do you know is this? It looks so confusing. Yeah, I was keeping track of which side, the right side and left side, and that's how I got to know where it is, but you don't have to believe me. Instead of having many functions like that, you can just put AND condition for each. So when you do this here, you're looking for a region where all these are true. So when you draw it, you get this, the one that I mentioned to you. So that's how you get it. And this region is only where, this is the only part that I want to see. So I can copy and paste it here. Okay. So end the function here, and then I will paste it. So then it's going to plot that part only for me. That's very nice. I didn't enter the cost here, but now I'm going to enter. So cost is $5 for the large one, so it's a 5x. And then you got to pay $2 for the small one. There we go. That's what I have. And this is the plot you have. Okay. Now to make it a little easier to see, I'm going to have a plot range so that I can show you better. Plot range is from, say, 0 to 65. So when I do this, this is the shape that you saw below is now showing up here. So why don't I show both here? What used to be was at the floor, that one. But if you put the cost for those, that's what you get up there. So what they're looking for is the cheapest one. So you're going to look for the lowest one. So if I see here from this side, let's make it a little bigger, then you can see it's this part. And that's the highest one, right? I can make it a little higher so that nothing is chopped off. 70 here. There we go. So which one is the lowest? It's this one. No matter from where you see, it is the lowest one. But why do we have to see? Let's go back. Earlier I told you, you got to look at only the vertices of this region and consider the cost. Why? Why not middle? Because this was linear, this function here. If they say squared here, then it's a different story. This could have curved like this, and the lowest could be in the middle. Then how do we find it? Oh no, we need calculus and other difficult things. So what do we do? The answer is they don't give you that problem. You're in high school, so you're all right. So they give you linear ones so that there's no magic happening in the middle. All the highest and lowest will be in the corner. So you go to the corner and then find it. Even going to the corner, you should know that if you move to the right, what you're saying here is you have the same box, same Y boxes, but you're getting more X boxes here as you go to the right. What does it mean? That you're getting more X boxes. That's what it means. The cost will go up. Take a look. As you go to the right, the cost is going up. Okay. What about between these two? It's hard to tell. Here I have more X boxes, fewer Y boxes, but here I'm getting more Y boxes and fewer X boxes. But X is more expensive, so probably going to the right is more expensive, and indeed, it was rising. But it was not so simple as this edge here. This edge was easy. You have the same Y boxes, more X boxes, so it's going to cost more. What about going this way? Walking this way is kind of tricky, because as you come this way here, I am getting less X boxes, but I'm getting more Y boxes, and there's a whole lot more Y. So it's about the same thing, so it's not so obvious how you should compute. So these are the locations. So you got to plug in you got to solve these equations to find it. So in other words, the only place that mattered were these two, right? So you got to find them, and then you got to find the values there and then plug in. So I will finish this job by telling you. So this one was this equation. Well, let's see. We are going to examine only these two places, right? So this one is y equals 3. And what was this guy? This one was y equals x. So shall we solve them? So x is 3 and y is 3. Okay. So what was the cost here? The cost function is this. Where did it go? It's this one, which I used here. So the cost is this, to which I'm going to plug in the solution here that I got. So if you plug in x and y into its place, in Mathematica it's done this way, then you get the cost is $21 for this spot. What about for this spot? Now you got to solve this one. 20x plus 10y equals 200. So shall we? Solve. 20x plus 10y equals 200. And then we are going to solve this one, which is y equals x. And the solution I get is this here. So now if I put the cost function, and then if I also put the solution I got into it, this is what I get. It's hard to see, so I will turn it into decimal. So I have this 46. However, can I have this 20 over 3 boxes? We cannot have a fractional boxes here. So if anything, we have to round it up. So what is 20 over 3? That's 6. And this is also, so 6 boxes each. Sorry, we got to get 7 boxes each. Okay. So if we use 7 boxes each, then let's solve again. I will do this one. So we are doing 7 boxes each. So in fact, I could have done this with a rounding, but it's 7 actually. 7. So the cost comes up to $49. So $21 win. So the best solution is here. And I'm kind of surprised that this is that high, because it didn't seem that high to me when I saw this function here. Was it that high? Where is it? I was seeing it. Here. They have about the same thing. I did something wrong. So let's find out. 5x plus 2y. And this one is 3. And I'm meeting with this guy. So here I'm meeting y equals 3. And this one was, I used the wrong function here. I should have used this. Okay, so I got this one here. And I got to round this up. So let's see. I have y equals 3 is all right. 17 over 2 is 8.5. So I should use 9. Okay, there we go. It's $51 if I used it. Whereas here is $49. So this is actually lower. So having a picture helped me. This, it goes down slightly. So the answer is here. The last problem would ask you how many of each you should get and how much do you pay. So the answer is you should get, where did it go? You should get 9 of the large one and 3 of the small one. Was it? No, here. You should get 7 of each and pay $49 for the minimum price. Now I will show you the power of this linear programming. Suppose the situation is such that they are doing a sale on the large boxes and the small ones became expensive. Then what do we do? The answer is this. You go here and you see this, except you have a different equation now. So you have to say the large ones are $2 and small ones are $5. And we want to know who is the lowest now. See, the story changes then. So I think it's clear that this one is the lowest point, and that's what you would get. And suppose the large ones are free now. What would happen? There we go. Not surprisingly, you would minimize using things that cost money. Take a look. We go all the way down to the right, right? And then in here, you could use either one of these to do the job. So in here, actually doesn't make any difference. Actually, I'm puzzled why I have so many different things here. But that's because it's free. So the answer is here. You could have more boxes and you would have fewer books in the box, but why bother, right? So this is what's happening here. So this one, where did it go? This one is the how many books you do. And if you go to the right side, then you have more space in your box. So the left side is exactly fitting the boxes, and you got to go for the grid because you got to have integer number of boxes. Let's see what if they actually pay you to use the box. For example, they pay you to use a large box. What happens? Then see you've already packed the book here, but you actually use more boxes so that you make money. So you use this one here, and then but you are limited by how many you are supposed to use. So you are limited to 15. So probably this number, but you're not. So you use 15 of them, but you're stuck by this. You got to use the small box 3. So you would use 12 of the large box and the 3. So here, indeed, it's a 12 of large box, and then you have 3 of the small box. So that's the money-making situation here. So now this time let's change it a little bit. Let's pay you even more. But I don't think you can do any better than that because I cannot even see it. Let me change this plot range so that we can see better. So I can go to -20. So here, why am I bouncing off? Oh, because I got surface here. So it's still, that's the answer. -12, 12 large boxes and 3 small boxes. Doesn't matter how much I pay. I'm stuck by this. I got to use 15 and no more. I got to use 3 and so on. But if I'm paying for it, that's another story. What if large box is expensive? Oh, then it got so expensive it kicked out of the price range here. Let me see. If I do $100, there we go. You would not use large boxes. See, you want to slide to the left and use this one here. So let's talk about the small box. Suppose you pay somebody to use small box. Then of course you would use as many small boxes as possible. Look at this. See, moving to the left is using more small box, and you use least large box, and so on. But once again, as long as you give linear functions here, you will have a flat surface. So I could change this pricing many different ways, and you will have different decisions to make. I could send the best decision to every corner here. Suppose I pay to use both here. I think it will dive in. Yikes, it's on the other side. Let me see if I go to -100. If I can see it. So I see it. Actually, did I dive it? Okay. I'm not sure if I succeeded. But there is a way to make any 4 of the 4 corners to be the champion. But the thing is, it will be one of those 4 corners, once again, because it's linear. So that's why it's called linear programming.